There's a motor spinning inside a wheel right now that engineers said couldn't exist. It weighs less than a car tire, produces more torque than a supercar, and solves a problem that's haunted the auto industry for over a century. And BMW just bet millions that it works. Here is why the new dual rotor technology might be reinventing the wheel. The problem everyone ignored. Every electric car on the road today carries a secret failure. Hidden under sleek exteriors and marketing promises of efficiency lies a system losing massive amounts of energy. Traditional electric motors waste around 25% of their power just moving it through complex drivetrains. Gearboxes, differentials, CV joints, and long drive shafts all steal energy before it reaches the wheels. That's not a small leak. That's a flood. For decades, engineers dreamed of an obvious solution. Put the motor directly in the wheel. No transmission losses, no mechanical complexity, just pure direct power. The concept makes so much sense that Ferdinand Porsche built a car with in-wheel motors back in 1900 at the Paris World Exhibition. It worked brilliantly. Then combustion engines got better, batteries stayed terrible, and the dream faded for 120 years. But the dream never really went away. Every few years, a company announces they've cracked it. They show prototypes. They promise revolution. Then nothing happens, because there's one brutal problem that kills every attempt: unsprung mass. When you add a heavy motor to a wheel, you're putting weight where it absolutely shouldn't be. Everything below the suspension, the wheel, tire, brake, and now motor, becomes unsprung mass. This weight crashes over every bump, making the ride feel harsh and unforgiving. Handling suffers noticeably. The suspension struggles to control the motion. It's like trying to jog while wearing cement boots, and the result compromises both comfort and safety. So engineers gave up on in-wheel motors. They accepted the losses from traditional drivetrains as unavoidable. They moved on. Then in 2021, a group of young German engineers decided everyone was wrong. They met at Technical University Munich's Formula student team, where they spent years obsessing over electric motor efficiency. After graduating, they did what ambitious engineers do. They joined large corporations. There they witnessed something that frustrated them to their core. The electric drive systems in production cars were, in their words, awful. Energy disappeared into heat and friction at rates that seemed unacceptable. One of these engineers was Dr. Alexander Rosen. He couldn't let it go. Neither could his colleagues. They kept meeting after work, running calculations, sketching designs in coffee shops. They weren't trying to improve existing motors by 5%. They wanted to tear up the rulebook completely. In 2021, they quit their jobs and founded Deep Drive. Their goal wasn't just ambitious. It was the kind of thing that makes experienced engineers laugh. They were going to build an in-wheel motor that actually worked. And somehow, they were going to solve the unsprung mass problem that had defeated everyone before them. What they created is now being called the most significant motor innovation in decades. But to understand why this new dual rotor technology might be reinventing the wheel, you need to see what's actually spinning inside it. The sandwich that changes everything. Most electric motors follow a simple pattern. A stationary part called the stator creates a magnetic field that spins a moving part called the rotor. The rotor sits either inside the stator or outside it. One stator, one rotor. That's been the standard design for over a century. Deep Drive looked at that design and asked a dangerous question: why only one rotor? Their answer became their breakthrough. They created a motor where the stator sits in the middle, sandwiched between two rotors that spin simultaneously. One rotor spins on the inside, one on the outside, and both work together in perfect synchronization. It's like having two motors occupying the same space, and the physics behind it changes everything. This configuration bridges seamlessly into their next engineering focus on structural elements. This dual rotor configuration dramatically increases the surface area where magnetic forces interact. More surface area means more torque can be extracted from a smaller, lighter package. The power density becomes almost absurd. Deep Drive's main in-wheel unit, the IW2000, produces 2,000 Newton meters of torque. That's 1,475 pound-feet per wheel. To put that in perspective, a Bugatti Chiron produces 1,180 pound-feet total. This single-wheel motor produces more. The entire motor, including its integrated power inverter, weighs just 34 kilograms, 75 pounds. Traditional in-wheel motors that attempted similar power levels weighed over twice that, which is exactly why they failed. Deep Drive's design isn't just lighter, it's light enough to actually work. But here's where the innovation gets subtle and brilliant. Traditional motors need something called a yoke, a large metal component that provides structural support and helps guide magnetic fields. The yoke adds significant weight without adding any power. It's dead weight you have to carry. In a dual rotor motor, the yoke becomes a problem for another reason. That chunk of metal would sit between the two rotors, creating distance and weakening their magnetic interaction. So Deep Drive made a radical decision: eliminate the yoke entirely. This created three new problems. Without the yoke, how do you maintain structural rigidity when magnetic forces are pulling in opposite directions? How do you cool the motor when copper windings generate intense heat? And how do you complete the magnetic field loops that make the motor actually work? The magnetic field problem solved itself. Because you have magnets on both sides, the north pole of one rotor connects directly with the south pole of the opposite rotor. The magnetic loops complete themselves through the air gap, no yoke needed. That was elegant. But structural support and heat management remained unsolved. And this is where Deep Drive's engineers created something truly special, something so clever that it's arguably more important than the dual rotor design itself. The secret lies in copper. The copper architecture. When Dr. Alexander Rosen discusses Deep Drive's motor, he begins with the windings. The heart of the technology, he says. The most important part is our winding. Most motors use copper wire for windings. It's flexible, easy to install, and functional. But Deep Drive needed something that could simultaneously generate electromagnetic force, provide structural support, and conduct heat efficiently. Wire couldn't accomplish all three. So they used copper bars. These bars form a truss-like structure, using geometry as strength. Like a bridge where triangular patterns distribute forces and create rigidity without excessive weight, Deep Drive's copper windings work identically. They create a self-supporting architecture that resists twisting forces when magnets pull from both sides. Each copper bar connects directly to the motor's housing, serving dual purposes. First, it anchors the windings mechanically, preventing warping under magnetic stress. Second, it creates a thermal pathway. Heat flows from the copper windings through the bars into the housing, where coolant fluid carries it away. This solution eliminates the traditional yoke, reducing weight. The copper bars provide the structural support and heat management the yoke previously handled. The design becomes lighter and more efficient simultaneously. The manufacturing implications matter equally. Complex motor designs often fail not because they don't work in labs, but because they can't be mass-produced economically. Deep Drive's copper bar architecture is simpler to manufacture than traditional wire windings. The bars can be precisely cut, shaped, and assembled with robotic precision without hand winding. This matters enormously for automakers. A brilliant motor design that's impossible to produce at scale is useless. Deep Drive's system is designed for mass production from the ground up, compatible with existing manufacturing lines without requiring new factory infrastructure. The patent images show copper bars forming intricate geometric patterns that are both beautiful and functional. These patterns represent thousands of hours of engineering, simulation, and testing to find the optimal configuration. When assembled, this copper architecture becomes remarkably efficient. The yokeless design reduces iron losses, meaning the motor wastes less energy at partial loads. Since real-world driving happens mostly at partial loads, not full throttle, this efficiency gain translates directly to increased range. But a brilliant motor design means nothing if it makes the car ride poorly. The unsprung mass problem still loomed large. They had an answer for that too. Solving the cement boot problem. The unsprung mass problem has ended more engineering careers than almost any other challenge in automotive design. Add too much weight to a wheel, and physics becomes your enemy. The suspension can't react fast enough. The tire loses contact with the road over bumps. Handling becomes unpredictable. This is why in-wheel motors failed repeatedly. Even if you could build a powerful motor small enough to fit in a wheel, adding 150 pounds of unsprung mass per corner made the car undrivable. Professional test drivers would return from demos shaking their heads. The concept was sound. The execution was torture. Deep Drive attacked this problem from multiple angles simultaneously. First, the dual rotor design's exceptional power density meant the motor could be much lighter than competitors. At 75 pounds per unit, including the inverter, it's remarkably light for its power output. But 75 pounds is still 75 pounds, and traditional wisdom said that was too much. Here's where Deep Drive's partnership with Continental changed the equation. Continental, the massive German supplier that makes everything from tires to brake systems, saw Deep Drive's potential early. Together, they developed something called an integrated drive brake unit. The brake components are built directly into the motor housing. Now the math changes completely. You're not just adding 75 pounds to the corner. You're replacing the entire conventional brake assembly at the same time. Traditional brakes, rotor, caliper, mounting hardware, weigh significant amounts. When you eliminate those and replace them with an integrated system, the net weight increase becomes much smaller. The second phase of their collaboration is even more significant. They're developing a completely dry braking system without any hydraulic components. This would eliminate brake lines, brake fluid, master cylinders, and all the associated hardware. The weight savings compound. But Deep Drive made one more crucial decision. For their in-wheel motors, they're targeting the rear axle first. On most electric cars, the front axle already handles the primary braking duty. The rear brakes are smaller, lighter, and less critical. Deep Drive's high power density allows them to dramatically reduce or even eliminate mechanical rear brakes entirely. Regenerative braking, where the motor acts as a generator to slow the car, can handle most braking force. Only in emergency stops would you need full mechanical braking on all four wheels. For normal driving, the rear motor generators provide all the braking force needed. Now you're not adding unsprung mass, you're nearly braking even. And because the motor weighs less than competitors attempted, the overall increase in unsprung mass becomes negligible compared to a traditional front-wheel drive system with conventional rear brakes. The engineers who said in-wheel motors were impossible due to unsprung mass weren't wrong about the physics. They were just working with the wrong motor design. This leads naturally into the performance metrics that demonstrate the full potential. When numbers tell the story. Deep Drive specifications tell a story about what becomes possible when you rethink fundamental assumptions. The IW2000 in-wheel motor produces 180 kilowatts of peak power. That's 241 horsepower from a unit that fits inside a 19-inch wheel. You could theoretically build a four-wheel drive car with 964 horsepower total, and the entire drivetrain would weigh about 300 pounds. Each motor delivers 2,000 Newton meters, which translates to 1,475 pound-feet. For comparison, a Ford F-150 Raptor's 3.5-liter twin-turbo V6 produces 510 pound-feet. One Deep Drive wheel motor produces nearly 3 times that. With 4 wheels, you'd have 8,000 Newton meters of total torque. That's enough to accelerate a 2-ton vehicle from 0 to 60 miles per hour in under 3 seconds, assuming the tires could actually grip. The limiting factor becomes tire technology, not motor capability. But raw power means nothing if the system drains the battery in minutes. This is where Deep Drive's yokeless design reveals its true value. Traditional motors carry significant iron losses, especially at partial loads. Every time magnetic fields cycle through iron components, energy dissipates as heat. This happens constantly during normal driving. By eliminating most of the iron, Deep Drive claims an 80% reduction. These losses drop dramatically. The motor operates more efficiently in real-world driving conditions. Highway cruising, city traffic, gentle acceleration. These are the conditions where drivers actually spend their time. And this is where Deep Drive claims a 20% efficiency improvement over traditional drivetrains. 20% might not sound revolutionary, but in electric vehicles, every percentage point of efficiency translates directly to range. A 20% improvement could transform a car with 250 miles of range into one with 300 miles. That's the difference between range anxiety and range confidence. The material usage numbers reveal another crucial advantage. Because the dual rotor design uses magnets more efficiently, deep drive needs only half the rare earth permanent magnet material compared to conventional motors. Given that rare earth prices have fluctuated wildly and supply chains remain geopolitically sensitive, this 50% reduction matters enormously to automakers. Similarly, the 80% reduction in iron means less weight, less cost, and less environmental impact. Iron might be cheap and abundant, but processing it requires energy and creates emissions. Deep drive claims their design delivers 30% lower cost per newton-meter of torque compared to conventional systems. But claims are easy, testing is hard. And this is where BMW enters the story, providing real-world validation. The company that never takes risks. BMW has built its reputation on engineering conservatism. They don't chase fads. They don't bet on unproven technology. They certainly don't let startups install experimental motors in their cars. Except they're doing exactly that with deep drive. The BMW Startup Garage program exists to identify promising technologies early. It's essentially a venture client program, where BMW acts as a customer for startups, helping them navigate the brutal complexity of automotive standards and production requirements. Getting into the program is difficult. Getting BMW to actually test your technology in their vehicles is nearly impossible. Deep Drive got in the door at the 2021 IAA Mobility Show in Munich. They had just founded the company. They had prototypes, but no production experience. They were unknown kids with a radical motor design. By all logic, BMW should have smiled politely and moved on. Instead, BMW's head of research vehicle concepts, Carol Versick, said something shocking. Deep drive could set new standards for e-mobility. That wasn't casual praise. Coming from a senior BMW engineer, that statement carried weight. BMW doesn't use phrases like "set new standards" lightly. They're not known for hyperbole. The collaboration progressed faster than anyone expected. Deep Drive's prototypes went through rigorous testing on BMW's test rigs. These are not gentle evaluations. BMW tests to destruction, pushing systems far beyond normal operating conditions to find failure points. Versick later commented that Deep Drive's prototype parts largely exceeded our specifications. He added, "That's really unusual at such an early stage and with a completely new technology." By July 2024, BMW announced they would begin road testing Deep Drive motors. Not on test tracks, on real roads, in real conditions, installed in actual BMW vehicles. Multiple variants would be tested to evaluate performance across different driving scenarios. This wasn't just validation. This was BMW betting its reputation that the technology works. If these motors failed dramatically during testing, it would reflect poorly on BMW's judgment. They don't take those risks without serious confidence. Continental's involvement adds another layer of credibility. Continental is one of the world's largest automotive suppliers. They've been building car components since 1871. They've seen every technology fad come and go. They don't partner with startups that might embarrass them. In 2024, Deep Drive's motor concept won the German Innovation Award. It wasn't just the judges who believed. The entire German automotive establishment was watching. And across the industry, other manufacturers were making phone calls to Munich. The material revolution. There's a silent crisis happening in the electric vehicle industry, and it has nothing to do with batteries. Rare earth permanent magnets power most EV motors. These magnets require neodymium, dysprosium, and other elements that are expensive, environmentally damaging to extract, and concentrated in supply chains that make automakers nervous. When prices spike, entire vehicle programs become uneconomical overnight. Traditional motors need these magnets in substantial quantities. The magnetic field strength determines torque output, so engineers pack in as much magnetic material as possible. It's a direct trade-off. Want more power? Add more magnets. Watch your costs explode accordingly. Deep Drive's dual rotor configuration breaks this relationship. Because the magnets on both rotors work together, creating overlapping fields that reinforce each other, The motor achieves higher magnetic flux density with less material. The magnet thickness in deep drive's rotors is surprisingly thin. Engineers who see the actual hardware often comment on this. They expect thick magnet sections. Instead, they find wafer-thin rare earth layers that still produce massive torque. The result? 50% less magnetic material. Cut your magnet usage in half, and suddenly your motor becomes economically viable even if rare earth prices double. This is strategic insurance against supply chain disruption. The iron reduction matters just as much. Traditional motors use substantial amounts of electrical steel in the stator core and rotor back. This iron guides magnetic fields, but it also adds weight and cost. More significantly, processing electrical steel requires energy-intensive manufacturing. Deep Drive's yokeless design eliminates most of this iron. 80% less steel means 80% less mining, smelting, and processing. The environmental footprint drops dramatically. So does the weight. Less weight means better efficiency, which means longer range, which means smaller batteries, which reduces costs further. The benefits cascade. There's a manufacturing elegance here too. Conventional motors require laminated steel cores, where thin sheets are stacked and bonded together. This process is complex and expensive. Deep Drive claims these material savings contribute to a 30% reduction in cost per Newton meter of torque. This metric matters because automakers don't just buy motors. They buy specific amounts of torque for their vehicles. A cheaper motor with less torque isn't necessarily economical, but a motor that delivers the same torque for 30% less money changes procurement decisions instantly. This cost reduction makes in-wheel motors economically viable for the first time. Previous attempts failed partly because the motors were too expensive to justify, even if they worked technically. Deep Drive is aiming to be both technically superior and cheaper than conventional drivetrains. If they're right, this new dual rotor technology might be reinventing the wheel in ways that matter more than just performance. The quiet revolution. Yannick Stamler, Deep Drive's product owner, makes a claim that sounds almost too good to be true. The motor, he says, is truly silent with inaudible noise and vibration. Electric motors are already quieter than combustion engines, but they're not silent. They whine. They hum. At certain RPMs, they can produce sounds that range from annoying to genuinely unpleasant. This matters more than you might think. One reason people love electric cars is the quiet. Any motor noise breaks that spell. Deep Drive's noise advantage comes from several design choices working together. First, the yokeless design eliminates magnetostriction, the phenomenon where iron changes shape slightly when magnetic fields pass through it. These microscopic shape changes create vibrations that propagate as sound. No yoke, no magnetostriction. Second, the copper bar windings have precise geometry that minimizes vibration. Wire windings can shift slightly under magnetic forces, creating tiny movements that generate noise. Rigid copper bars, locked into a truss structure, don't move. No movement. No vibration-induced noise. The integrated brake system adds another benefit. Traditional disc brakes produce significant noise, especially during regenerative braking transitions. The switch between regenerative and mechanical braking can cause jerky behavior and sound. Deep Drive's integrated system allows seamless blending, making transitions imperceptible. This silence matters for luxury applications. Premium automakers charge substantial premiums for refined driving experiences. NVH, noise, vibration, and harshness. Engineering is obsessive in high-end vehicles. If Deep Drive's motors truly are silent, they become attractive for luxury EVs where buyers expect perfection. The plug-and-play flexibility matters too. Deep Drive offers both in-wheel motors and central drive units using the same core technology. Automakers nervous about in-wheel concepts can use the central drive configuration and still gain efficiency benefits. This flexibility lowers the barrier to adoption. For the in-wheel configuration, you gain package space. Without a central motor, transmission tunnel, drive shafts, and differentials, the interior space opens up dramatically. You could lower floor height for easier entry. You could expand the cabin. You could increase cargo capacity. The proportions of the vehicle can change fundamentally. This is where the promise gets really interesting. Current EVs are often just modified versions of combustion car platforms. The skateboard battery layout improves things, but the basic form factor remains constrained by tradition. True in-wheel motor designs could enable completely new vehicle architectures. Autonomous pod vehicles with lounge-style seating, delivery vans with walk-through cargo areas, urban microcars with surprising interior space. The possibilities multiply once you eliminate the central drivetrain. But all of this remains hypothetical until these motors enter production. And that's where the timeline becomes critical. The future arriving now. Deep Drive's timeline is aggressive. Small-scale production by 2026, mass production by 2028. That's 5 years from concept to market in an industry where new component technology typically takes 8 to 10 years. You need extensive testing, supplier qualification, manufacturing validation, and proof of reliability over hundreds of thousands of miles. Mistakes cost billions and destroy reputations. Deep Drive compresses this timeline through their BMW partnership and Continental collaboration. BMW provides real-world testing. Continental brings manufacturing expertise. These partnerships accelerate what might otherwise take a decade. First applications will likely be all-wheel drive add-ons for existing EVs. A manufacturer with front-wheel drive can add Deep Drive's in-wheel motors to the rear axle, creating all-wheel drive without redesigning the entire vehicle. It's plug-and-play. Initial customers will probably be premium brands willing to pay for differentiation. As production scales and costs drop, the technology migrates to mass-market vehicles. If every new EV gained 20% efficiency from better motors, the impact on battery demand, charging infrastructure, and operating costs would be massive. Deep Drive has raised over $53 million from serious investors. BMW I Ventures and Continental are strategic investors making calculated bets on technologies they intend to use. Whether it succeeds commercially remains uncertain. Automotive history is littered with superior technologies that failed for reasons having nothing to do with technical merit. But for the first time in decades, in-wheel motors are taken seriously by major automakers. That's a bigger deal than you think. What do you think? Could in-wheel motors finally become reality, or will they remain a perpetual next big thing? Drop your thoughts below and subscribe for more engineering deep dives.